Okay, is momentum conserved when shooting a shotgun? Well, what do you think? Certainly. The explosion of the powder causes the shot to move very rapidly forward, right? So a shotgun typically has a bunch of little BBs in it, right? And you shoot it, and then you're trying to hit that clay target that's flying, right? They come out at a very high velocity. Now the shotgun itself, though, is going to weigh, is going to have a certain amount of mass to it, right? So quite a bit more than just this little bit of shot. So what happens is the shot comes out. Well, it's going to have smaller mass, high velocity, and then the shotgun. Well, if it's up against your shoulder, it's briefly going to have some velocity, but it's going to be an impulse. It's going to be force. It's going to be a force times time, right? It's going to hit into your shoulder. But it's momentum also, because the shotgun has a mass, and it has a velocity, right, initially, and then but then it's very short lived, because your shoulder is gonna take the brunt of that. So if the gun is free to move, it will recoil backward with a momentum equal in magnitude to the momentum of the shot, right? So these two, the two values of momentum are the same. It's a vector. Right, so this one is going in this direction, it's minus. That one is going that way. We've chosen that to be plus. Okay. Okay, and I already said all that. So, okay, they're just giving some tips. So, and we'll let you worry about that one. Okay. Yeah, so this is interesting, right? So it's how do you say the system? If you're only considering the shotgun and the BBs coming out, the pellets coming out, if that's only the system, well, then this shotgun is going to bounce back. But a person typically is sitting there holding it, right? So that changes the system, right? So you want to think about what is your system. So now that system is this shotgun isn't going to recoil any sort of distance. It's just going to recoil a bit, but then your body is part of the system, and your body is part of the mass, right, in your shoulder, and so it gets more complex that way. Okay, right, and it can get more and more complex. So we'll leave it at that for now. Okay. Okay, yeah, it can get more and more complicated depending how you're thinking about it, right? All right, and I think I said all that. Yeah, you could keep, right, you're standing on Earth, and it can get more and more complex. We're not going to worry about that. So, okay, so this is good. This is what I like. So you have a rocket in space, okay? This is real, because we all know there's spacecraft all over the place, right? Our buddy Elon is shooting rockets, but they've been, rockets have been going up in the air for a long time, and we've had objects in space orbiting the Earth since 1958, I believe. 58, yeah. How does a rocket accelerate in empty space when there is nothing to push against? Well, okay, so we're going to go over that. This is a good question. The exhaust gases rushing out of the tail of the rocket have both mass and velocity. Therefore, they have momentum, right? So you have exhaust gases coming out. Now they're kind of small. This is a big, heavy rocket, but they're going really fast, right? The momentum gained by the rocket in the forward direction is equal to the momentum of the exhaust gas in the opposite direction. Now, typically what happens is it takes the rocket time to speed up, right? If the rocket is just floating up there in space, well, this blasts out at a very high velocity right away. And then that's inertia, right? This rocket has mass, it has inertia, it's sitting there. That's Newton's laws. And then and then it's going to be gaining momentum as the velocity increases, right? So we have that concept as well, okay? But they're always they're the same, right? They're the same because you have yeah, they're the same. So they push against each other. That's why if you have a rocket in space, it doesn't need to push off planet Earth or anything. It will go just floating up in space because the exhaust gases and the rocket push against each other. So in space, this rocket will move. It's not just going to sit there. And you're thinking, well, it's not pushing against anything. No, this right at this point here, this gas is going this direction and the rocket is going that direction. They're pushing against each other. That's all you need. Yeah, Newton's third law, Newton's law is always applied. So, okay. Elastic and inelastic. So if you throw a ball, you know, against the wall, it's going to bounce back. But if you just had some clay, right? When we were kids, we'd have clay and we'd make things, right? We didn't have internet. We had real toys. So clay was one of our toys and we'd make stuff. But of course, I had brothers and you know, you start throwing the clay and then our mom would get mad. But if you throw clay against the wall, it'll just stick. Plop. And if you have a ball of clay, it just flattens out. It just sticks. Plop. So all that momentum, it's not elastic. It's very inelastic. It doesn't bounce. It just goes plop and sticks to the wall, right? And the clay will deform and the wall, you know, we'll feel that pressure, right? And it might warm up. If you had a little thermometer, it would heat up a little bit, right? So the energy would be dissipated that way. Okay, so what is the difference between these types of collisions? Well, we have a feel for that, but of course in physics class we're going to quantify that. Is energy conserved as well as momentum? Well, I just talked about that a little bit. So we're going to talk about inelastic collision. So the objects do not bounce at all. So here they're going to use an example. We talked about football players previously where the football player hung on to the other one. So he didn't bounce off them. They hung on and then they were a unit, right? Now railroad cars have a little hitch there. So what'll happen is that if this car is moving and he bumps into all these cars, well, they're not going to bounce off because this little hitch is going to hitch on, and now they're all connected. So it's kind of like when the football player hung on to the other football player, right? Okay, I'll put this up here. You can freeze frame and you can do this yourself if you want to. I recommend it. You can stop the video and do this on your own if you want to. But so okay. Okay, we talked about kinetic energy in previous chapter. So, all right. Okay, so elastic, and here's what I want to get to. Elastic and inelastic collisions. So energy is not conserved in a perfectly inelastic condition. So inelastic, that's like the football players hung into each other. If you throw clay, it just sticks, plop, right? It doesn't bounce. So it's inelastic. If the objects bounce apart, instead of sticking together, the collision is either elastic or partially elastic. Most things that we deal with are partially elastic because things will deform. Energy is used, you know, a tennis ball deforms and then so that's energy. So it's not going to bounce back at exactly the same amount that it hit with, right? An elastic collision is one in which no energy is lost. A partially inelastic collision is one in which some energy is lost, but the objects do not stick together, right? And then the greatest portion of energy is lost in a perfectly inelastic collision when an object sticks. So if I have a wad of clay and throw it against the wall, once it sticks, the energy is lost, right? It deformed, the energy went into deforming the clay, it hit the wall, maybe it vibrated. There's some sound, you would hear that, so it vibrated the air. That took some energy, it may have warmed up just slightly, right? So that's where the energy would have dissipated into, all those sorts of things. All right. And let's go through this. We kind of already said that.